Good morning, students. In earlier classes, we have discussed about the definitions of Laplace transformations, the Laplace transformation of various functions. Now today we discuss the various properties of the Laplace transformations. So some properties of Laplace transformations are properties of Laplace transform. The first property of Laplace transformation is the linearity property. This property says that if the Laplace transformation of functions fi x with respect to parameter p is equals to fi p, then the Laplace transformation of c1 f1x plus c2 f2x plus cn fnx, where with respect to parameter p where c1, c2, c3 and cn are constants, this is equals to c1 Laplace transformation of f1x with respect to p, and c2 Laplace transformation of f2x with respect to p, plus cn Laplace transformation of fnx with respect to p. And this can be written as ci Laplace transformations of f(i)x with respect to parameter p, and we can write this one as ci fi. So by using this property, which is known as the linearity property, we can find the Laplace transformation of some functions, and we can also write that this one as minus also. We can also find the Laplace by using this property. We can also find the Laplace transformations of these functions, which are the sum or subtract of the two functions or many more functions. So this is known as the linearity property. The second property is known as change of scale property. Change of scale property says that if Laplace transformation of fx with respect to parameter p is equals to fp, then Laplace transformation of e raised to minus ax fx with respect to parameter p is equals to f of p plus a. This is known as the change of scale property. And this change of scale property, rather this one is known as first shifting property, not change of scale property. This is known as first shifting property, not change of scale property. First shifting property. The proof of this property is, as we know that Laplace transformation of the function e raised to minus ax fx with respect to p, by definition this is equals to integral 0 to infinite e raised to minus px into e raised to minus ax fx dx. This can be written as integral 0 to infinite e raised to minus p plus a into x fx If we compare this by the definition of the Laplace transformation, we see that this is the Laplace transformation of a function fx with parameter p plus a. So this can be written as Laplace transformation of a function fx with respect to parameter p plus a, and this can be written as f of p plus a. So the Laplace transformation of e raised to minus ax fx with respect to parameter p, which is known as the first shifting property, this comes to be as the Laplace transformation of the function fx with respect to parameter p plus a. Similarly, we can find the second shifting property which says that if Laplace transformation of a function fx with respect to parameter p is equals to fp, and we define another function gx, this is equals to, if we define the another function gx which is equals to f of x minus a and 0, f of x minus a when x is greater than a, and this is 0 if x is less than a. Then the Laplace transformation of gx with respect to parameter p, this is equals to e raised to minus ap into f of p. This is known as the second shifting property. We can see the proof of this theorem as we find the Laplace transformation of gx with respect to parameter p. By definition, this is equals to integral 0 to infinite e raised to minus px gx dx. And since gx is defined in the different intervals, so we can break this interval as integral 0 to a gx dx gx e raised to minus px dx plus integral 0 to a to infinite e raised to minus px gx dx. Now, if we use the definition of the function in different intervals, we get Laplace transformation of gx with respect to parameter p is equals to integral 0 to a 0 e raised to minus px dx plus a to infinite f of x minus a e raised to minus px dx, which comes to be integral a to infinite e raised to minus px f of x minus a dx. If we put x minus a is equals to t, then dx is equals to dt, or x is equals to a plus t, then this integral changes as integral 0 to infinite e raised to minus p into x a plus t f of t, or we can solve this one as e raised to minus ap comes out to be out of the integral 0 to infinite e raised to minus pt ft. If we compare this by the definition of the Laplace transformation, here we see that integral 0 to infinite e raised to minus pt ft dt is nothing but the Laplace transformation of a function fx. So this is equals to e raised to minus ap Laplace transformation of fx with respect to parameter, and we can write it as e raised to minus ap f of p. This is known as the second shifting property. We can write the this property in another alternative form, and which form can be written as alternative form of this property. Alternative form of second shifting property. The alternative form of the second shifting property is, if fb with the Laplace transformation of fp with the Laplace transform of fx, if fp with the Laplace transformation of fx, then e raised to minus ap, then e raised to minus ap into fp be the Laplace transform, be the Laplace transform of form of f of x minus a into h of x minus a. E raised to minus ap, fp be the Laplace transformation of a function f of x minus a, h of x minus a, where h of x minus a is the Heaviside unit function. So in alternative form, the second shifting property can be written in terms of the Heaviside unit function. So these are the three properties of the Laplace transformation. Another property is also well-known property, which is the change of scale property. We earlier discussed about that. Change of scale property. Change of scale property. This property says that if Laplace transformation of fx with respect to parameter p is equals to fp, then the Laplace transformation of f of ax with respect to parameter p is equals to 1 upon a f of p upon a. This is known as the change of scale property. We can prove this property by taking the definition of the Laplace transformation, which shows that the Laplace transformation of f of ax with respect to parameter p, by definition this is equals to integral 0 to infinite e raised to minus px f of ax dx. If we put ax is equals to t or x is equals to t upon a, then dx is equals to dt upon a. So substituting this value in the Laplace transformation, we get Laplace transformation of f of ax with respect to parameter p is equals to integral 0 to infinite e raised to minus p, x comes to be t upon a, f of t dt upon or this is equals to integral 1 upon a integral 0 to infinite e raised to minus p upon a into t f of t dt. If we compare this by the definition of the Laplace transformation, we see that this integral is the Laplace transformation of a function ft or fx with respect to parameter p upon a. So we can write this one as 1 upon a Laplace transformation of a function fx with respect to the parameter p upon a. Or we can write it as 1 upon a f of p upon a. This is known as the change of scale property. We can use these properties in solving the various problems of the Laplace transformations. First, if we find the Laplace transformation of a function x plus 2 whole square e raised to x with respect to parameter p, we will use these properties in solving these type of the problems. We see here that first we find the Laplace transformation of a function x plus 2 whole square with respect to p. We can write it as the Laplace transformation of x square plus 4x plus 4 with respect to parameter p. Or by the using of the linearity property which we have discussed earlier, we can write it as the Laplace transformation of x square with respect to parameter p plus 4 times Laplace transformation of x with respect to parameter p plus 4 Laplace transformation of 1 with respect to parameter p. As we know that the Laplace transformation of a function x raised to n with respect to parameter p is equals to factorial n upon p raised to n plus 1. So using this Laplace transformation of x raised to n, we find that the Laplace transformation of x plus 2 ka whole square with respect to p is equals to, by using this definition, we get the Laplace transformation of x square is equals to factorial 2 upon p cube plus Laplace transformation 4 times Laplace transformation of x is factorial 1 upon x p square plus 4 times Laplace transformation of 1, Laplace transformation of 1 is factorial 0 upon p. So this comes to be 2 upon p square plus 2 upon p cube plus 4 upon p square plus 4 upon p. This is the Laplace transformation of x plus 2 ka whole square. Now we have to find the Laplace transformation of x plus 2 whole square into e raised to x with respect to p. If we take this Laplace transformation as fp, then using the first shifting property, we see that the Laplace transformation of e raised to minus ax fx with respect to parameter p, this is equals to f of p plus a, where fp is the Laplace transformation of the function fx. So using this first shifting property, we find that this is equals to Laplace transformation of x plus 2 whole square is given by f plus p, this one fp. So we get the Laplace transformation of x plus 2 whole square e raised to x p. This is equals to the Laplace transformation of x plus 2 whole square with respect to parameter p plus a. P plus a, here p plus a is minus 1, so p minus 1. So putting these values in the Laplace transformation, we get 2 upon p minus 1 whole cube plus 4 upon p minus 2 whole square, p minus 1 whole square, sorry, plus 4 upon p minus 1, which is the required Laplace transformation of this function. So in this problem, we have used the linearity property and then the first shifting property. So we have discussed about the various properties of the Laplace transformation, and by these properties we have simplified a problem by using these properties. In next class we will see some properties of Laplace transformation and various transformations of the differential functions and the integral functions also. Thank you very much.